Hello everybody, happy Friday. I am still with the DECA students in Washington, D.C., and today we actually do need to learn some material, so I thought I'd go back to our trusty format of doing some guided notes together. So in front of you, you should have some guided notes for section 3.5, which is all about zeros of polynomials. Now the first thing we need to look at before we even start talking about zeros is reminding ourselves what factored form of a polynomial looks like. Now we saw this last week, so this shouldn't be new, but let's go ahead and fill in. When we see factored form of a polynomial, it might have a dilation in front, and then depending on the degree of the polynomial, we might have 2 roots, or we might have 3 roots, or we could even have 4 or 5. So because I don't know exactly how many roots there are, I'm going to put ... at the end, and then maybe just remind myself that the degree of the polynomial is going to equal the number of roots. So that's a nice way for me to figure out how many roots I'm supposed to have. You heard me mention the word roots quite a bit there, but what we were talking about in our section title was zeros of polynomials. So we're going to do a quick review of what it means to be a zero. So a zero, or a root, which is why I can use the words interchangeably, of a function is a value for which the function equals 0. So if I take my function and I plug in my root, whatever my root is, I should get a value of 0. If the 0 happens to be a real number, then the 0 is also known as an x-intercept, which we also saw last chapter when we were talking about quadratic functions. If it's not a real number, we just have to call it a 0 or a root. So how do we find the zeros or the roots for polynomials? As a quick review, back in chapter 2, we found zeros of quadratic functions using 4 different techniques. Our first technique that we saw was to graph on the calculator and identify x-intercepts that way. Now that was a really nice strategy when we had the graphing calculator, but one problem that we encountered then, and that we will continue to encounter, is that it won't show us the non-real roots. It will only show us the real roots. Other methods that we have for finding zeros back in quadratic functions was we could factor. Now factoring was probably our best technique because it was a little bit faster and also involved less work. The only downside is quadratic functions are not always factorable. Our other 2 strategies were completing the square and the quadratic formula, both of which always worked, but the one downside to them is that they were a little more time consuming. So how do we find zeros for higher degree polynomials? Polynomials with degree bigger than 2. We really only have 2 strategies. The first one is to graph again on our graphing calculator and identify x-intercepts that way. Although we run into the same problem we did with quadratics, it will not show us any of the non-real roots. Our second method is to factor. And we saw some factoring techniques for polynomials back in section 3.3, things like sum of cubes and difference of cubes, and we will continue to use those, but we will see a new factoring technique today called factoring by grouping, which should sound familiar. So our first example problem today won't involve any factoring, but we are going to use what we know about factored form to try to sketch the graph of a polynomial. So in example 1, you see a polynomial in front of you written in factored form, and we're going to use both the intercepts and the end behavior to sketch a graph. So the first thing I'm going to do is just make a note to myself about what the x-intercepts are. Now when I look at this in factored form, I see 3 different places where my function might equal 0, which means I have 3 roots. Since all 3 of them involve real numbers, I know that I have 3 x-intercepts. One of them is when x is 0. That's this first one. One of them is when x is 4, which is the second one. I'm just using the zero product property. And my third one is -3. So we will continue to use the zero product property like we saw back in chapter 2. I can also find the y-intercept. Now I technically already know it because if there's an x-intercept at 0, 0, it has to be the y-intercept. But the way that I can find it is I can plug in that x is 0, and whenever x is 0, I discover that y is 0. So that makes my y-intercept. I'm also going to go ahead and talk about the end behavior. Now, when looking at this polynomial, even though I don't want to actually expand it, imagine that we did x times x times x. We would get a leading term of x cubed. Now, we should know what x cubed graphs look like. They're going to go down on the left. They're going to go up on the right. So my end behavior has two statements. As x approaches infinity, y, or in this case, I'll use f of x approaches infinity. And as x approaches negative infinity, f of x also approaches negative infinity. Now, using all of these things, I should be able to sketch a graph. So the first thing I'm going to do is put down my x-intercepts. So let's see, I have one of them at -3. I have one of them at 4. I have one of them at 0, 0, which is also my y-intercept. I'm going to go ahead and label this just so I know what these values were. And now that I know my end behavior is supposed to go down on the left, this should go down. It's going to have to come up and have a smooth maximum. Remember that polynomials can never have sharp turns. We would never see that in a polynomial. And then it must go down, have a smooth turn in order for it to continue up. So there's a sketch of this polynomial. Notice that we have no idea how high this maximum is. I don't know what the y value is at each of these extrema. All I know is that they occur somewhere between when x is 0 and when x is 4, or between -3 and 0. So we're going to get to use factored form a little bit more in this next example. We're told that polynomial p of x has zeros at -2i and 3. And part A says, if it is known that p of x is a third degree polynomial, meaning it must have 3 total roots, we learned that back in chapter 2 from the fundamental theorem of algebra, can we figure out what the other 0 is? So remember back in 3.4, we learned that if we have a non-real root, its complex conjugate also has to be a root. So I know right away that positive 2i must also be a 0 of this polynomial. In part B, I'm told the y-intercept is the point 0, 6, and now we want to try to write an equation in factored form. So remembering what factored form looked like, I don't know what the dilation of p of x is, but I do know that I have a root at 2i, I have a root at -2i, and I also have a root at 3. The reason I was given this coordinate point 0, 6 is I can take it and I can plug in 6 for y, and I can plug in 0 for x. So everywhere that I see an x, I'm going to plug in a 0. And then we just get to simplify it. This is going to make us go back and remember, how do we simplify when involving I? But let's just take it piece by piece. So I look at the first one. 0 minus 2i is just -2i. 0 plus 2i is 2i. 0 minus 3 is -3. It's all being multiplied by a. So let's see if we can multiply it all together. Well, -2i times 2i is going to give me -4i squared. I still have -3 out front. I know that -4 times -3 really gives me 12. So now I have a times 12i squared. But we know that I squared is the same thing as -1. So this is really -12. So if I divide both sides by -12, it looks like a was -1/2. Now that I've found a, I can write my equation in factored form. Factored form shows me all of my roots, whether they're real or non-real, I can see all of them. For our next example problem, we're going to try to factor our polynomials to identify the roots. So in the first problem, even though it's a cubic, I notice that every single one of my terms has a greatest common factor of not just a 4, but also an x. So I'm going to factor out a 4x. I look at what's left over. I have an x squared plus x minus 6. This trinomial that I'm left with, I should be able to factor pretty easily by now because we did this a lot back in chapter 2. I'm going to put it into two groups. I need to multiply to get negative 6. I need to add to get 1. So it must be x plus 3, x minus 2. Now that I've factored it, I can identify the zeros by setting y equal to 0. And taking each one of my factored pieces and setting them equal to 0. This is us using the zero product property. So maybe this first piece equals 0, maybe the second piece equals 0, or maybe the third one. So I'm going to have 3 different zeros. One of them is 0, one of them is negative 3, and my third one is 2. All of them are real, so I could also call them x-intercepts. All right, let's take a look at problem 2. This problem is going to allow us to use some factoring techniques that we saw back in 3.3. Because it's a binomial, I first think about this might be a difference of squares or it might be a difference of cubes. The way that I figure out this is a difference of squares is because I can write x to the 4th as something squared, namely x squared squared. And I can write 81 as something squared. It's 9 squared. So I'm going to go ahead and start writing it as a difference of squares. So remember, difference of squares took each square root. One is a plus, one is a minus. Now you might be thinking to yourself that this is it, but when I keep looking at this a little bit closer, I notice that again, x squared minus 9 is a difference of squares. This time, it's x squared minus 3 squared. So again, I can break this one up and do x plus 3, x minus 3. When I look at this first one, this is a sum of squares. So I can factor a sum of squares by taking each one of my squares. So I have x squared and I have 3 squared. And when I factor it, I use the same numbers as before, but now I'm going to add in an I. So it's x plus 3i and x minus 3i. So now that it's completely factored, I can set y equal to 0. I have all of these different pieces that might equal 0. So if I set each one individually to 0 using the zero product property, I would get that x was plus or minus 3i. Those are my two non-real roots. And then x is plus or minus 3. Those are my two real roots. It makes sense that I had 4 roots because it was a 4th degree polynomial. So we're going to go ahead and stop this video here. Go ahead and play the second video and continue on the back page.